So,
how many cylinders are we gonna have this quarter?
I don't know yet.
Can you make it a lot?
There's no way that is right. Look at what they did.
Shh, quiet. Average value means the average Y value. So if I have a function, I've got higher Y values over here. I've got lower Y values over here. And the average Y value would be somewhere in the middle. So we have a formula to calculate the average value. If a function y is equal to f of x is continuous on the integral from a to b, then we define the average value of f from a to b to be 1 over b minus a times the integral from a to b of f of x dx.
I got really good at drawing these little integral things. I used to be.
You're going to go far in your calculus life then. This makes sense because whenever we find an average, we add everything up and then divide by the total, which is all we're doing here, right? The integrals, the sum of all of it, and then we're dividing by the difference in the bounds from the beginning point to the ending point. So example 1 here says, find the average value on the function from -1 to 3 without integrating. Apply your knowledge of geometry, assuming, of course, that we remember something from geometry. So we have a piecewise function. Whenever I am integrating, I am finding the area under the curve. So I need to find the area under the curve from -1 to 3. This is a rectangle or a square that's 2 by 2. So the area is 4. I've got 2 triangles with a base of 1 and a height of 2. So my areas are 1 each. So here we go. Applying my formula. I've got 1 over the first bound minus, or the second bound minus the first, 1 over b minus a. And then the integral from -1 to 3 of my function. So I've got 1 over 3 minus a minus 1. So this gives me 1/4. And then the value of this integral will be the area under the curve from -1 to 3, which is 6. So this is saying that the average value on this interval is 1.5, which is a reasonable value. If you look at the values of y, okay, there's 2 all along from 0 to 2 there, and this goes from 0 to 2. So 1.5 is a reasonable answer in this case. Okay, so now let's do one with a function where we have to integrate. It says, given f of x is equal to 1 over x on the integral from e to 2e, find the average value of the function on the interval using antiderivatives. So I need to find the average value. So I've got 1 over b minus a gives me 1 over 2e minus e. And then I have the integral from e to 2e of 1 over x dx. Okay, so this is 2e minus 1e, which gives me 1e. So I've got 1 over e. And then now I need to integrate. What is the antiderivative of 1 over x dx? It's the natural log. So I've got ln of x evaluated from e to 2e. And this 1 over e is multiplied times all of it. So I'm going to plug in my bounds and then distribute. So I've got 1 over e times the ln of 2e minus the ln of e. And let me distribute just a little bit. So this will give me 1 over e natural log of 2e minus, what's the ln of e?
I don't know. 1. It is 1. I know it's 1 for a fact 'cause I missed this question.
It's not 0?
No, it's not.
It
0.
doesn't just go away?
It does not just go away.
I mean, because a lot of my students just like make it go away.
I mean, that was essentially, but now it's one.
Okay, we're sure it's 1.
We're sure.
All right. So I have 1 over e times 1, which gives me that. And I'm going to leave it like that.
It's hard.
So the 1 over e ln 2 would simplify any further.
I would leave it. I mean, if that were e squared, then yes, it would, but leave it like that.
Wait, why
Wait,
is it not just -1?
Because this 1 over e is multiplied times 1.
Oh,
It's
yeah.
distributed.
Oh.
Can I have your?
Why you put bounds on that one, but not the other one? Like you put from 2e to e on for 8,
I did put that right here.
or the straight line one.
He's asking why did ln x bounds
Yeah, that,
right?
And not here?
No,
Yeah.
down. He's just showing that that's what we need to happen. That's the next step. So like the one right below it basically is saying the same
I'm sorry, I'm still confused about what you're asking. Can
No,
you-
no,
thing. He's asking why you have.
the one you put the straight line here went over there.
Attendant, please.
Okay. Well, because they asked me to find this without integrating. And so when I do that, I'm just finding the value under the curve. Okay. In other words, if I could do that, but I would have to split all of these up. I would have to integrate this function from -1 to 0, and then integrate this from 0 to 2, and then integrate this from 2 to 3. But that's a whole lot of work, right? I'm just finding this 6 is equivalent to this line right here and this next problem.
So why do we do anti-derivatives instead of just what we did before?
I'm confused about what you're asking. Oh, okay, the difference. Okay.
We did something different on the first one, didn't we? Like we like.
Okay, the difference, here's the difference. All, this is all we did. When you anti-differentiate, when you integrate, all you're doing is finding the area under the curve.
Okay.
So this is saying, this second problem, the area under the curve in the first problem was 6. The area under the curve from e to 2e is given by this line, 1 over e natural log of 2e minus 1 over e. Okay. But conceptually, you are finding the area under the curve when you anti-differentiate, which is different from the fundamental theorem of calculus, which is what we just had the quiz over. Okay, but we'll get to that. Right now, part B says find the average rate of change of the function on the given interval. Okay, so let's go back to earlier in our course study. Average rate of change is just the slope.
Yeah.
So when it says to find the average rate of change, all I'm doing is finding y2 minus y1 over x2 minus x1. So in this case, they want me to find the average rate of change on the interval from e to 2e. So I need 2 y values and 2 x values, and I subtract. So I need f of 2e minus f of e over 2e minus e. All it is the slope from e to 2e. So f of 2e, I'm going to take 2e and put it into my function. So I'm just going to replace the x with 2e. So I've got 1 over 2e minus, I take the e and plug it in, 1 over e. And then on the bottom, in the denominator, I've got 2e minus e, which is just 1e. So, two different things that we are looking at today. The first is average value. Average value is given by this formula, 1 over b minus a times the integral of the function. And then average rate of change is just the slope from point to point. So, question so far?
No sound.
Let's look at the next page. And before we get into some applications, I want to go over and think about conceptually certain things using some units. So we're going to think about the units for acceleration, velocity, and position using meters and seconds. So if I have the integral from A to B of the acceleration, if I integrate the acceleration, what do I get? I get the velocity evaluated from A to B. So this would be V of B, plugging in the bounds, minus V of A. The antiderivative of the acceleration is the velocity because what's the derivative of the velocity? Acceleration. Therefore, the antiderivative of the acceleration is the velocity. And the units work also. Here's how the units work. I have acceleration, which is meters per second squared. And then this dt tells me that it is with respect to time, and time is in seconds. So I have meters per second squared times seconds, which gives me meters per second for my velocity. Okay, so look at this one. If I integrate the velocity, I get position. Again, because the derivative of the position is the velocity. So this would give me x of t evaluated from A to B. And then I plug in the bounds. I got x of b minus x of a. And looking at the units again, I should end up here. If it's position, I should end up with meters. I've got velocity, meters per second. And then the d of t gives me time seconds. Those cancel. I end up with meters. So if I integrate the position,
Oh snap.
I have no applications for that. Okay. And I did this right here to set up what we were going to do next. Okay. So I need you to stay with me here so that this does not get confusing. So what would the following compute? I need you to go back at your notes on the first page and tell me what this is. This is an average value.
Yeah.
It's an average value of a function.
Okay.
What is my function in this case?
Acceleration.
The acceleration. So this is the average value of acceleration. Okay, let's do the next one. What is this? This would be the average value of the velocity. And this would be average value of the position. Well, now let's think about the units. Ignore the 1 over b minus a for just a second. And look at the example that we just did. If I integrate the acceleration, what do I get? I get meters per second. But then I am dividing by b minus a. And so b minus a are the bounds, and the bounds, dt, is the time. So what I have here is I have meters per second, and then I divide by seconds again, and I get meters per second squared. And that makes sense because what is this? This is an average value of what?
Acceleration.
An acceleration. Everybody okay with that?
Wait, so you multiply meters.
Okay, so when I integrate the acceleration, I get a velocity. That's what we did right here, right? but then I'm dividing by b minus a, where b minus a is the difference between the bounds. And the bounds, it's dt, the bounds are time. So like from 0 to 3 seconds, for example. Okay, so if I integrate the acceleration, I get velocity, but then I'm dividing by the time. So I have meters per second squared in my final answer. Does that make sense? Is everybody okay with that? Okay, well, let me ask you this. What does this compute? First of all, what is this? This is a slope, right? Look back on the first page. It's the average rate of change of what?
Velocity.
Of the velocity. The average rate of change of velocity. What does it compute?
Meters per second squared.
I've got meters per second over seconds, meters per second squared, which is an acceleration. It has to be, right? Because we learned this is a slope. Or another way to say that in calculus terms, it's a derivative. And what's the derivative of the velocity? It's the acceleration. Okay, so what I'm saying is that the average value of the acceleration and the average rate of change of the velocity are computing the exact same thing. They both give me an acceleration. Think about it, okay? I integrate the acceleration and then divide by the time. So I get a velocity divided by time. And here I have a velocity divided by time.
So does that mean you can use them like interchangeably?
Yes,
Oh.
depending on the information that I am given, which we will get to, okay? But let's do this. If I integrate the velocity, I get a position and then I divide it by time. So I have position divided by time, which is a velocity. Well, this is equivalent to x of b minus x of a over b minus a. This is the average rate of change of position. And these two things are equivalent to each other. Why? Look at the units. I integrate the velocity and I get position. And then I divide it by time. So it's position over time. Here I have the same thing, position over time. So what I'm saying is that depending on the information that they give you, there may be two different ways to calculate the same thing. Okay, either by finding, if I'm looking for an acceleration, I could find the slope of the velocity, or I could find the average value of the acceleration. Let me put some numbers in there and show you. Okay, so I have three equations. I have a position equation, 3t squared minus 4t. If I take the derivative of that, I get the velocity, 6t minus 4. If I take the derivative of that, I get the acceleration, 6. For simplicity, let's consider the time period from 0 to 2 seconds. So the first one says, find the average rate of change of position. Whenever you see rate of change, that is the slope. So I want the rate of change of the position, x of b minus x of a over b minus a, y2 minus y1 over x2 minus x1. And look at the units. I have position divided by time. So the slope of the position gives me a velocity. Yes? So now plug in the numbers. This gives me x of 2 minus x of 0 over 2 minus 0. So now I want to take 2 and 0 and put them into my position equation. I plug in 2, so I get 12 minus 8, which is 4. Plug in 0, and I get 0. So I've got 4 divided by 2, which is 2. And let's put the units on there. Again, it's position over time. So 2 meters per second. Questions on what I just did?
Where'd you get 4? 0. Which question?
So I take, this is x of 2. So I'm going
Oh,
to
I
take
see,
2 and
I
0
see.
and
Oh,
put them into the position equation right there and simplify. Okay, well, I said previously that this is the same thing, it's right here, as the average rate of change of position is the same thing as the average value of the velocity. So now let's find the average value of velocity. Okay, so that's going to be 1 over b minus a times the integral. So average value velocity. So I've got 1 over b minus a, so 1 over 2 minus 0, which is 1/2. The integral from 0 to 2. And here I need my velocity, right? And so my velocity, specifically in this instance, is 6t minus 4 dt. Okay, so the 1/2 stays here. The antiderivative of 6t is,
Wait, isn't it gonna be the same thing though?
it is, but I want to show you that it works. The antiderivative of 6t is 3t squared. The antiderivative of -4 is -4t, and it's evaluated from 0 to 2. This gives me 1/2. I plug in 2. That's going to give me 12 minus 8, which is 4. I plug in 0 and I get 0. So I have 1/2 times 4, which is 2. And this is a velocity. It's an average velocity. So my units are meters per second. It works. Well, let me do one more example here. This says find the average rate of change of velocity and then find the average value of acceleration. So average rate of change of velocity, it's the slope of the velocity. And the slope of the velocity is the derivative of the velocity, which gives me an acceleration. So the average rate of change of velocity is going to be v of 2 minus v of 0 over 2 minus 0. And let's look at the units. I've got meters per second over seconds, or meters per second squared. So to get v of 2, I'm going to take 2 and plug it into my velocity equation. Okay, and so my velocity equation was 6t minus 4. I plug in 2, so I get 12 minus 4, which is 8. Minus, I plug in 0, and I get -4, which gives me 12 over 2, so 6 meters per second squared. Well, now let's find the average acceleration, okay? And so when you see this question, especially on the AP exam, sometimes they will leave off the value of, or they might just say average acceleration, okay? Whenever you see that, average acceleration, that means 1 over b minus a times the integral. So again, if you see average rate of change, that is slope. Average acceleration is going to be 1 over 2 minus 0 times the integral from 0 to 2. And this time my acceleration function, and my acceleration function is 6 dt with respect to time. Okay. The antiderivative of 6 with respect to time is going to be 6t. evaluated from 0 to 2. So this gives me 1/2 12 minus 0 or 6 meters per second squared. So let me summarize what we just did. Okay, we have two different things. We're either finding the slope, the average rate of change, or we are finding the average value, where we do 1 over b minus a times the integral. However, going back up here, the average value of acceleration is equivalent to the average rate of change of the velocity. If I take the derivative of the velocity, I get an acceleration. If I'm finding an average value of acceleration, I also end up with an acceleration. The average value of the velocity is equal to the average rate of change of the position. So let's look at a couple of examples. An oil tanker runs aground and immediately begins to spill oil. Unfortunately, it happens, like oil tankers run into Alaska, right, and start dumping oil into the bay there. The number of gallons, G, remaining in the tanker at time t in minutes is given by the equation G is equal to 400 times 20 minus t in parentheses squared. What is the average rate of flow of oil from the tanker from t is equal to 1 to t is equal to 3 minutes? Okay, so if I am working this problem, the first thing that I want to think about is the information that they give me. And if we think about it in terms of physics, position, velocity, acceleration, I either have a number or a quantity, a rate, or a rate of change of a rate. So what is this equation? G equals, is it a number? Is it a rate? Or is it a rate of change of a rate?
Rate, it's a rate number.
It's a number. It's the number of gallons.
It's a gallons in the relations to rate
It's a number,
This is a number.
but it literally says rate.
given by the rate.
I'm not there yet.
That's the question.
What is this? That is the question. What information do they give me? What is G? G is a number. Therefore, this is the position.
Oh, that's stupid.
I know it is the position because it says it is the number of gallons. It is not a rate. It is a quantity. The question that they ask, however, it says, what is the rate of flow of oil? So what are they asking for?
Rate of change.
They're asking for the velocity because it is a rate of flow of oil. So now, how will I go about answering the question? Well, there are two ways.
Yeah, easy way and the hard way.
I am going to find the slope of the position or the average value of the velocity. So the first way would be G of 3 minus G of 1 over 3 minus 1. This is position divided by time, which gives me the rate of flow or the velocity. Or I could do the average value of the velocity, which would be 1 over b minus a of the integral from, I wrote that wrong, a to b. Of v of t dt. In this instance, you can do what you want, right? But I am going to use this first one. Why? Because that is the equation that they give me. Could we find the velocity? Well, sure, we could take the derivative of that, right? But we are card-carrying calculus slackers. We want to just skate by with the least amount of work possible and still get the right answer. So we're going to use the first one. Okay. Let's look at it, another example.
Are we gonna do it?
No. We're just gonna set it up.
So with this, are we like in the calculus jungle where there's like no calculator?
It could be both. Okay. So example 3 says an elevator is being tested and travels from floor to floor without ever opening its door to pick up people. During the time interval from t between 0 and 60 seconds, the elevator's velocity v, measured in feet per second, and the acceleration a, measured in feet per second, are continuous functions. The table below shows values of these functions at selected times. So in our table here, we have selected values of velocity and selected values of time. And it says approximate 1/40 times the integral from 20 to 60 of v of t dt using a midpoint approximation with 2 subintervals and explain its meaning in terms of the elevator's motion using appropriate units. So in this case, I am not integrating a function because I don't have an equation. What they're asking me to do is to take a midpoint approximation. So I'm going to do a Riemann sum. And remember, right Riemann sums, left Riemann sums, midpoint Riemann sums, and the trapezoidal rule, all of those are approximations of the integral, the area under the curve. So I've got 1/40, and then I'm going to do a midpoint approximation. So be careful here, because where does it start?
20.
It starts at 20 and it goes to 60. And I am using 2 subintervals. So the first subinterval goes from 20 to 40. The second goes from 40 to 60. So when we are doing Riemann sums, we're just finding the area of rectangles, which is width times the height. The width of the first interval is 20. The height I find at the midpoint. The midpoint of 20 and 40 is 30. So the height is given by this value of 10. The second interval is also 20 wide. It goes from 40 to 60. And the height is going to be the value at the midpoint, which in this case is 5. So I've got 1/40. This is 200 and this is 100. So times 300. 4 goes into 37 times with the remainder of 2. So 2/4 is 1/2. So I have 7.5 for my approximation.
Wait, so how'd you do the 10 and 5 for the?
Okay, so since this is a midpoint approximation, the first rectangle goes from 20 to 40. What's the midpoint of 20 and 40? 30.
Oh, okay.
What is the height at 30? 10.
So,
And this one, the height is 5 because the midpoint is 50.
so your warning is basically don't look at points in between, look at the numbers.
Correct.
Wait, no, the midpoint's like in the middle, 30 and 35, isn't it?
No,
You're
that's
just-
what he.
You're
No,
looking
that's
at
what I'm
visual.
saying, okay?
The number between.
Look, Jacob, it goes from 20 to 40. What's the middle?
Oh, okay.
30.
That's whack.
And the middle here is 50.
Why do you put 1/40 in the beginning?
Because of that right there. They're asking me to approximate this. Okay, so I'm not done yet. All right, but let's put units on here. What did I just find? I integrated the velocity, which gives me position. And then I divided it by 40, which is the seconds. So this is a velocity feet per second. So now they asked me to explain its meaning in terms of the elevator's motion using appropriate units. Okay, so now what did I just find? What is this? This is the average value of the velocity, right? We look at that on the first page. So I can say the elevator averaged, what did it average? 7.5 feet per second from t equals 20 to t equals 60 seconds. And we cannot say, and get credit for the justification, we cannot say 40 seconds. Why not? Which 40 seconds? The first 40 seconds? The middle 40 seconds? The last 40 seconds? Be specific. So here's what you need on the justifications for full justification credit points. You need the number 7.5. You need the units, feet per second. And you need the time from this to this. It's the nut. Number, units, time. So, very last thing we're going to do here.
Sure.
Just a little quick summary / review. Keeping it straight. Given that we have a function, f of x is x squared plus 4x, give the setup for the following. I have the integral from 0 to 3 of x squared plus 4x dx. So here I integrate 1/3 x cubed plus 2x squared. And then I evaluate from 0 to 3. And I would plug in my bounds and then subtract those two things.
Oh, okay, yay.
The average rate of change of the function, that average rate of change is the slope.
Yeah.
So in this case, I would need f of 3. I'm finding the slope on my function from 0 to 3. So f of 3 minus f of 0 over 3 minus 0. And then finally, we have the average value of the function on the interval from 0 to 3. Okay, so average value of the function is 1 over b minus a times the integral. So I've got 1 over 3 minus 0 times the integral from 0 to 3 of f of x dx. And f of x is x squared plus 4x dx in this case.